good morning or afternoon, whichever works for you. Uh, I am Priyank. I start by thanking the organizers for inviting me here, or well, for having me here. So, what I'll be talking about is coherence-gated quantum devices, and this is more towards the superconducting quantum computation. So, it's something that we want to use what you have been hearing a lot about these quantum materials. And on the right hand side here, you're seeing is an actual device that is a qubit connected. I mean, the critical component here is actually two Josephson junctions. We'll look at the zoomed part of that in a while. And this here, which is not running somehow, is the simulated version of what we see in this case, like a bookkeeping map. So with that, I would like to take a couple seconds for this description. So we are relatively a new center that I have joined, say, around 7 months before. It's called Center for Quantum Science and Technologies in IIT Mandi, and that's the beautiful north campus of IIT Mandi. And that right there is somewhere we are located. And of course, right now we are focusing on quantum sensing, computation, and communication. And there are more activities as well. So you can take a look at the web page of the CQST homepage. All right. So because I'm rather fresh coming to India after maybe just for 7 months, so I'll just tell you what do I do exactly. I'm an experimentalist, and frankly speaking, there should be a question like how much experimentalist I am, and that answer is here. This is how much experimentalist I am. That is actually I'm ready to make something that you see on this screen. So this thing what you're seeing is an ultra sensitive bolometer. It has capacity to detect 10 photons worth 10 gigahertz. So just to give you a brief idea, is like if it was, if you are standing on moon and clicking a photo from here, that's the noise it will pick from that detector. So that's around about we are talking. And the dimensions that you're seeing here is around 200 nanometers, which is about, say, if you have hair, you cut it 1,000 equal thicknesses, and one thickness is that. And the elegancy is putting all of them really side by side. And this thing is a consequence of 5 days of rigorous work. And that right there is the zoomed in version of something you know as a qubit, the Josephson junction, the critical component of a qubit. And these arms are made of aluminum, and in between somewhere we have also put some 2 nanometer of oxide. All right, what do we do with that? We put it in something like this, what we call a sample holder. There are RF lines where we can throw in a lot of electrons going up and down in really high frequencies, couple billions per second, something like that. And just for you to have a scale, this around is a centimeter. And then this thing actually sits into something that's more tricky, is this device that we call dilution refrigerator, where the temperature reaches around 10 to 20 milli-K. And this is the primary requirement. So all that is maybe rather cheap, but this is something that's worth million. So kind of a trade-off. So if you want to look a bit more detailed about what I do, is described in my website. And no need to worry about all these letters. You will find a QR code at the end of the presentation. All right. So qubits, right? So that's the core component of any quantum processing unit. So before we go on, we need to understand some basics of it. Any kind of system, a quantum system that can host two eigenstates or two energy eigenstates, I can attribute these eigenstates to be 0 and 1 and make a qubit out of it. The beauty of this thing, or say the only reason why we are worried about all this, is for this system to host something we call superposition. So a classical system can host one state at a time. This system attains both of them in the same at the same time. And we have come up with something more curious, or say more intelligent, that's block sphere, where we represent this kind of notation. So where we have different components, and if you just do a little bit of jiggling around the polar coordinates, you would see that any state that is landing on this block sphere can be represented by the phi and theta, or maybe in this formulation to be more precise. And that kind of sums it up, that you can have a qubit, and the Hilbert space of it can be represented just by this block sphere here. And then we can drive it and of course read it out what the state of this qubit is at the end of the day. And why is it important? Because without the manipulation, there's no computation. So that's key component of any computer. All right. With that, somehow this simulation doesn't work, but okay. So the deal is that this block vector is something that is the representation of your qubit state, how pure it is. If it is landing on the surface of this block sphere, that means it has quite fair contributions from sigma x, sigma y, sigma z, which means it has fair superposition of 0 and 1. However, the moment it starts to land 0 and 1, then it's a precise energy eigenstate, either it's in ground state or else it's excited state. And when I say that it is sitting on the surface, that's where the whole coherence is, that's where the whole superposition is. And I need you to keep this in mind, because that's something which is critical to the whole discussion that we'll be keeping afterwards. All right. Of course, I'm borrowing a lot of stuff from quantum Mac, and this is a discussion about quantum materials. So this is something which is, I think, a fair assumption that you know about it. We can represent this qubit in the form of density matrix, where these diagonal terms will actually represent the excited ground and excited states, or vice versa, the way you want to put it. And then the off diagonal terms are the one which represents the superposition, the key property of any quantum device, the coherence. And this is what we'll be interested in. But okay, that's something that you can also figure out after doing a little bit of math, that this is a geometric term. It's sigma x square plus sigma y square square rooted overall. And why this is important? Because everything related to quantumness, be it superposition, entanglement, communication, anything that you want to do, this is the thing that you want to use as an advantage over any classical system. So that's why this is important. But there's one problem with this kind of stuff, which is decoherence. Anytime you have a qubit, you have two levels of energies. You prepare the state in coherence, in some coherence, that means a linear superposition of the two. It decoheres. It talks to the environment, and it just lands into one of these energy eigenstates, either the 0, 0 or else 1, 1. And that kind of starts to destroy your whole computation game. And you want to get rid of that. But hold on. Before we go on, I want to change, I want to impress upon this fact that the off-diagonal terms is the one which we care about, the quantum coherence part. However, I'll take a bit of detour now to tell you that a simple representation of this equal superposition between ground and excited state could be something much simpler. Okay, this thing doesn't work. Never mind. All righty, now it's yes. So beam splitter. The thick red line here actually represents a beam that is incident. This is our beam splitter, and the thinner lines are actually representing the transmitted and the reflected, transmitted and the reflected beams. What it shows you is that this could be a way to mimic the 50-50 combination of ground and excited state. This is just a bookkeeping, so we could do it here as well. However, if I want to do a quantum computation, what I want is I want to play with this ratio. Maybe I want to make it 49-51 or maybe 60-40. But in order to do that classically, like this experiment, what do I need? I need to actually change this beam splitter. And is that very pragmatic to make a quantum computer, that you have an operator who is sitting, and then every time you want to change the component, you will have to actually physically change the beam splitter? It's not practical. To solve that issue, there are many works, and now it's like a range of work which people have done around this, is to couple a qubit with something of a photon source, which you can in turn call a photon router. So if the qubit is in ground state, you actually push this simulation is not okay. So if it is in ground state, your photon actually goes to the detector 1, and if it moves to excited state, your photon actually goes to the other side. Here, what the interesting part is that these two are somehow coupled in a way that if I prepare a different linear superposition of these two, ground and excited state, then the photon here will also be going in different probable combinations, and which was the key. That means you can now relinquish the beam splitter, the physical traditional beam splitter, and now you can work with these kind of photon routers to create quantum network, to create quantum computation and whatnot. But hold on. Every time you measure the qubit, you projectively measure. And this means you kill the coherence. So the quantumness is gone. What you're using right now is rather a destruction of the state that you prepared. That was your advantage, which is where I actually pose a simple question. What if I had a photon router which works on how much coherence does my qubit have, instead of asking which energy eigenstate was it in? And that brings me to this specific protocol, where what I do, it's actually very much inspired from the superconducting quantum computation. So we have a qubit where we can couple different aspect of it, with say sigma x and sigma z, and then we can read out two different currents at the same time. And then we have FPGA, where we can actually reconstruct the conditional density matrix, which will become evident in a while. And on the basis of this conditional coherence, conditional density matrix, I can call something or say define something what we know as coherence score. And if the score is larger, we send the photon connected, which is this source which is coupled to the qubit, it actually goes to the port A, and if it is smaller, it goes to port B. That's a very nice photon router. However, you would come back and ask me, okay, you are measuring the qubit, you are also going to collapse the state of the qubit. But no, we are not going to do that, because what we are going to use is weak measurement. So both of these parameters that are being tested for the qubit is in the limit of weak measurement. That means you're not strongly projectively measuring it, but rather peaking it little. So that way you kind of preserve the coherence as well. Okay, does that work? So before we go on to the guiding equation, we need to look at the ingredients. What ingredients do we have? That's the Hamiltonian we have. We couple x and y, so we have a Rabi oscillation around x-axis. So your qubit is in the Bloch sphere rotating around x-axis, and then this z component gives you that every time you are measuring this one, it's gonna push it towards your energy eigenstates. So that's our Hamiltonian. And then we define the coherence score. This coherence score is nothing but the L1 norm in the z eigenbasis. And coherence, of course, by definition is an energy eigenbasis parameter. So in case of energy eigenbasis, you have sigma x square plus sigma y square. I'm calling it conditional because this is what it will become once we have the weak measurements going on. And then, of course, the homodyne current, this is what we measure. So we can model our current which we are measuring from the qubit in the following fashion. This is the white noise term, and then this is the measurement rate, like how fast am I measuring, and this is the measurement efficiency. And it will become evident, because if I start to increase my efficiency, it will start to become an actual projective measurement. Decrease it, and your noise basically tells you that your qubit will be alive as far as it's not being tested. So with that, and this part, routing rule is something that I already told you, that if it goes larger or smaller, we'll just route it differently. Okay, with that comes the master equation, the stochastic master equation. That's the heart of my whole scenario, which is the qubit being seen as an open quantum system. So what you have here, the first term tells you that for any quantum system, if you have density matrix, this is how it will evolve. But because this is a qubit, it can relax, the energy relaxation, and it can dephase. Both of these terms contribute to the decoherence. And of course, this term is something that is dissipation, which comes about when you are measuring the qubit. However, there is one more thing that is the key to any kind of quantum system, and that's called back action. So this is the term that's capturing the back action part, where you see that there eta and gamma k, both of them are there, and gamma k is basically dependent on x and z. You reduce the efficiency of your measurement to 0, and the back action immediately turns to 0. So your equation is kind of consistent in the Ito formulation. With that, we go to simulate this whole equation for, say, roughly 3,000 trajectories. And what I'm presenting here for you is just to reduce down. Even this one looks quite a bit, because there are 10 trajectories. I'm looking at the average of these 10 trajectories. What's going on in this scenario is that I define that there is a capital T. So from start to capital T, I keep monitoring the qubit multiple times in a weak measurement fashion. However, each time when I measure it, I actually look at what I got, feed it into the master equation, and then I get another kick. That means another measurement to the qubit, and I keep repeating that. If I do that, what I observe is that my qubit actually is persisting the coherence quite a bit. This is my threshold which I set, and that's 0.7. So 70% of the time, my qubit is coherent. That's the answer I get. And if I do not care about what I measured. I just simply measure once, I measure twice, thrice, like simple measurement, and I just average them all. What happens then? Standard quantum mechanics. Your coherence completely falls. So your qubit is basically being projectively measured then. So that sort of sets the rule that if you have a quantum system and you want to call it really a quantum system on the fly, what you would do, you would apply this protocol and basically weekly measure it for a certain period of time. And then on the basis of measurement, you keep modifying your measurement protocol and see what is coming out. And if your coherence score is large enough, you would say that, okay, the system is quantum enough, go on and do the quantum stuff you want. So that's like a standard protocol. And this distribution here actually is for all the 3000 trajectories, where you see that indeed many trajectories survive this threshold of 0.7. All right, so that kind of sets the stage that weak measurements can indeed tell me, without destroying the coherence of the qubit, whether it is coherent enough or not. So one more thing that I want to just impress upon, of course, the more detailed version of this you will find on this article. Well, not really article, it's an archive version of it. So it's still in the peer review. But okay, here's something which is important, because I know the coherence and the picking of collapse into 0 or 1, both of this is purely random. That's the key feature of quantumness, right? Which means I can make a quantum random number generator using the same protocol, just the same qubit. But now I'm not talking about projective measurement, rather keeping the coherence and making a random number generator out of it. What I want you to have the feel for is something H infinity. That's the entropy that you get for the maximum probability for a quantum system. And in our case, because our probability will be 1, well, max probability will be 1 plus or minus r by 2. And if you feed in the r, which is block vector, basically, it gives you this. This term here actually is S threshold, which we defined. So you just plug it in and you realize that this is your H infinity. So it gives you a theoretical bound. And we did this simulation for another 3000 and sometimes a million trajectory as well. And we found out that this bound is never broken, with certain caveats, which you can figure out in here. Now the deal is this. So I want you to have this idea that this threshold, the coherence score, is now being given as a knob in an experiment. So if I put the threshold to be 0.3, which means I say I don't care much about the quantumness. If it is 0.3, it's fine for me. I see out of 3000 trajectories, almost 90% of the trajectories are there, but the probability distribution is rather large. So the bound which you are talking about, the H infinity, is not so good for you. However, if you want it to be really, really nice, so you set your threshold score to 0.9, and now you see that maybe 10% of, or less than 10% of the trajectories only pass through. You sacrifice a lot, but what do you win? The certification. That means at the end of the day, the measurement or any protocol that you're running, you know for sure that it is 90% times quantum enough for your game. And if you want it to be 1, why not? So the trade-off is basically there. With that, I bring you back to square one. We had the question that, okay, we were making photon routers on the basis of energy eigenstate of the qubit. So what did we have there? Of course, the decision variable was on the qubit excited qubit energy eigenstate, and the projective readout was killing the coherence, and it was heralding. It was telling you that photon was there, but it was not telling you whether the photon was quantum enough coupled to the qubit. However, these things is something that gets wind over by this coherence gated protocol. So you have the decision variable, that's the resource for you in the experiments, and the weak readout actually gives you the certification for the coherence. With that, you have quality certificate, and of course, there is implementation for this in furthermore games. What I could explain a bit more, but more is detailed here. The deal is that we could use this protocol in quantum repeaters, network, and more so if we could phase track the photons, then that could also be used for long range quantum network, including the repeater. So there are things which we can do with this protocol. And something I want you to take home with is this kind of measurement scheme. So I have a qubit, I want to use it as a sensor. I couple it with a sample by a virtue of, say, a conditional interaction switch, which means I turn on and off interaction on the basis of this certification. So that is the condition. Now I measure the qubit, I perform this weak measurement protocol, and I see that okay, in 90% time my qubit is actually quantum. So I turn on the interaction, let it interact with the sample, and then I make the measurement. And inferences will follow, of course. What is the advantage you have? The advantage is this threshold knob that you got, and that actually starts to imprint on the idea that if I just keep changing the efficiency, thereby I get different back action. I can study what measurement back action does indeed to the quantumness of the device. And then, of course, we can talk a little bit more about environment-induced classicality. Like even if I set my threshold smaller, the environment is pushing it more. So, of course, I get more classicality. Whether this one is at play or the other one is something that can be understood using this whole protocol. With that, I think the conclusions are pretty much there. I wouldn't be repeating those. So if you get it, fine. Not otherwise, you can catch me. And that would be the end of talks. Thank you. And I actually want to thank this guy here. He is my postdoc friend. And the fruitful discussion that started with him was, Priyanka, I don't understand it. And then somehow I try to convince him. And well, that's about it. This is the QR code that will take you to my website. Thanks a million.
Thank you so much. Questions, comments, queries?
Yes, please. The way you want.
So, in your weak measurement protocol, do you have problem of weak value amplification? Like, is that going to be an issue in the process that you will?
Okay, maybe this is where I mixed up. I am a experimentalist, but all you saw here was theoretical stuff. It's a simulation stuff. I joined 7 months before, so I don't have my experiments here. It happens in Finland. So this is on the go, and we will know when we start doing the experiment. So that is something that's on the go.
I guess my standard question would be, do you have to do a post-selection process?
No, the idea is that we relinquish that part, and we will be doing this live on the go. So you don't have to do the post-selection. Worries. Please.
What is the typical coherence time?
Louder.
That's a good question, actually. The typical coherence time.
Can you repeat the question?
So he's asking what's the typical coherence time of the qubit.
Coherence time.
So up until say an year ago, the qubit coherence time for superconducting qubits were around 100 to 200 microseconds. But recently we developed a recipe there we can go up to a millisecond. But in the worst case scenario, 500 microseconds is nowhere to be gone. But this is something that is achievable. This is aluminum oxide, and aluminum. Yes.
Very well. Any further input? Then I will move on to
Thank you.
3 short presentations. 10 minutes each.